Welcome back, folks. We'll get ready with the afternoon session. Pleased to have Sanghamitra Dutta presenting on algorithmic fairness from the lens of causality. Take it away.
Thank you so much for having me here today. So today I'll be presenting my research on algorithmic fairness, which synthesizes tools from causality and information theory. In particular, an emerging body of work within information theory called partial information decomposition. So I'll start with the motivation. So machine learning is entering into almost every aspect of our lives these days, including these really high stakes applications such as hiring, education, lending, healthcare, etc. For instance, roughly 40% of companies today are using machine learning to assist in various stages of their hiring process. So while these models are really great at learning all patterns present in the data, but blindly learning all patterns can sometimes lead to unintended consequences, like propagating biases with respect to gender, race, age, nationality, etc. that can have serious undesirable consequences on people's lives, and in many cases is also disallowed by law. So when it comes to addressing these legal disputes or even informing policies and interventions, only identifying bias at the output of a model is not always sufficient. And we really need to dig deeper and understand another important question that bridges both fairness and explainability. That is, how do we identify and explain the sources of bias in machine learning models? So let us understand this question through an example. We consider a scenario of hiring a software engineer for a safety critical application. We have a bunch of input features that go into a model, and the model decides whether to hire or not. Now, these features could be things like coding test score, aptitude test score, etc. Now, the first thing to do is to avoid biases with respect to gender, race, etc. We stop using these sensitive attributes as inputs to the model. But again, it has been found that even if we do not use them explicitly as inputs, the output could still be strongly correlated with gender or race because the other features are correlated. And the legal motivation for this is also disparate impact, which refers to policies or practices that affect some group of individuals more adversely than others, even if it is not intentional. But then sometimes there are some features that are more important than others. Like coding test score might be really critical to the hiring of a software engineer. This is where it becomes important that how did the disparity arise? Did it arise primarily due to the coding test score, or were the other features also responsible? And even the law says that disparate impact may be exempt if it can be justified by an occupational necessity. Like coding test score may be critical for the software engineering job. Weightlifting ability may be critical in the hiring of firefighters. But then aptitude test may not be critical, as in this landmark court case of Griggs versus Duke Power. So this motivates a problem that I'll state informally now, that given a choice of critical features, how do we say if the disparity is exempt or non-exempt? And towards answering this question, my work provides a systematic measure of non-exempt disparity, which is the bias that is not justified by the given critical features. So algorithmic fairness in general is a growing field of research with several interesting works in the last few years. The problem that I'm interested in is that of understanding these feature-based contributions to disparity. And I'm trying to quantify this non-exempt disparity using partial information decomposition and causality, which has received less attention. So my outline for the talk will be something like this. I will be spending most of my time on this problem of finding a measure of non-exempt disparity. And after that, I will briefly touch upon some other related problems that I'm also working on. So I will now start with this problem statement and some notations first. So let Z denote the protected attribute like gender, race, age, etc. Then we have a bunch of features that will go into a model. And the model output is denoted by y hat. Now the critical features will be denoted by xc. And all the other non-critical or general features are denoted by xg. And we also assume that there's an underlying causal model or data generation process which generates all of these features, where these U1, U2, U3 are some underlying latent factors that we do not usually observe all the time. Now the problem statement is, given a choice of critical features, what is a good measure of non-exempt disparity, which is the bias that cannot be justified by critical features? Now, once we have such a measure or definition, it could be used either for auditing, that is to check if there's any non-exempt disparity present or not. It could also be used during training, for instance, as a regularizer with the loss function to selectively reduce the non-exempt disparity. But before we get there, the question is, what is a good measure of this non-exempt disparity? Now, to answer this question, we adopt an axiomatic approach where we first look at some canonical examples and try to arrive at some desirable properties for such a measure of non-exempt disparity. These desirable properties then lead to one measure that satisfies these properties. But this measure requires causality and knowledge of the underlying causal structure. So we also propose some observational relaxations that do not require the knowledge of the underlying causal structures all the time. And then we also use these measures to perform some case studies that can sometimes also inform our choice of examples and properties. Now, the significance of this approach is that these canonical examples really distill some paradoxical scenarios that can arise often in the context of, say, hiring, where a candidate measure may fail to correctly capture what we would intuitively like to capture in a measure of non-exempt disparity. And in doing so, we also expose the pros and cons of several candidate measures. So I'll start with some popular definitions of fairness, that is statistical parity and equalized odds, and discuss their pros and cons. So statistical parity, I guess many of you might already be familiar with, is statistical parity says that the model is fair if the output is entirely independent of the sensitive attribute like gender, race, etc. And the information theoretic measure of statistical parity is mutual information. I'm including the definition of mutual information here, but what this basically quantifies is the statistical dependency between the sensitive attribute and the final output. But statistical parity has been criticized that it can sometimes accept applicants who may not meet the critical necessities. Like if we again go back to our example of hiring software engineers for a safety critical application, let's assume that the critical feature is correlated with the sensitive attribute where the other features are not. And let's say we use something like a linear, we are training a linear classifier and using this statistical parity as a regularizer with the loss function. Then what could happen is, to reduce the mutual information between the sensitive attribute and the final output, the model may significantly reduce emphasis on the critical feature. So if this is like the classifier that we learn without using any kind of fairness criteria, but if we try to incorporate statistical parity as a regularizer, the model might end up being something like this, which reduces the emphasis on coding test score entirely, which is not desirable. To resolve some of these issues of statistical parity, another popular definition is equalized odds, which is that the output is independent of Z, conditioned on the true labels Y. And a perfect classifier would always satisfy equalized odds. But there are also some criticisms centered around equalized odds, which say that agreement with these historic labels can sometimes propagate biases that are already hidden in these labels. So we again go back to the same example. And this time, let's say the aptitude test score happens to be correlated with gender. So this is let's say the points are all perfectly separable, and we learn a perfect classifier using these historic labels. But then this could still be criticized because here the disparity that we observe is arising due to aptitude test score, which is not really a critical feature. So the problem statement, our problem statement adopts a middle ground between these two extremes like statistical parity and equalized odds that uses some domain knowledge to identify which features are critical. And then we question that what is a good measure of non-exempt disparity, which is the bias that is not justified due to the critical features. Now, to find a measure of non-exempt disparity, the first candidate measure that we consider is conditional dependence or conditional mutual information. That is, among the candidates with the same value of coding test score or condition on the coding test score, there is no further dependence between Z and the final output. And the information theoretic measure for this is conditional mutual information, which essentially captures the conditional dependence between Z and Y hat given the critical features. But then in this work, we make an important observation that conditional dependence can sometimes falsely detect bias or misleading dependencies, even when a model is causally fair. And to understand this, we look at a counter example of a causally fair model. So this time again, we have this feature coding test score. Now, this is the simplest possible representation for the coding test score, which also happens to be correlated with the sensitive attribute. Here, Z denotes a sensitive attribute and U denotes a latent random variable, which is inner ability, which is independent of the sensitive attribute. And let's say the aptitude test score happens to be just U. And the model basis it is able to distill out this true inner ability and take decisions entirely based on U. So such a model is causally fair because the output Y hat does not vary with Z after fixing this inner ability U. And this is a reference for causal definitions of fairness, which essentially say that the model is fair from a causal perspective if the output Y hat does not have a causal influence of this sensitive attribute Z. So this is a scenario which is fair from these causal definitions of fairness. But then if we look at this kind of conditioning on critical feature kind of approach, here conditioning will say that the mutual information is greater. That is, given the critical feature, the Z and Y hat are not independent. That is, this conditional independence does not hold for this particular example. So this motivates a desirable property that the measure of non-exempt disparity should be 0 if the model is causally fair. So to summarize, we found that conditional mutual information or conditional dependence does not satisfy this causal fairness property. And it is this limitation of conditional mutual information that leads us to examine this emerging body of work in information theory called partial information decomposition, which further decomposes conditional mutual information into two components called unique information and synergistic information. And I'm going to define these quantities shortly. But what we find is that this unique information quantity satisfies our causal fairness property as well as some others. So what is this unique information? Before formally defining it, I'll try to intuitively explain the idea through some examples. So we look at these two examples here. For the example on the left, XC is Z plus U and the output is just U. So here the output Y hat doesn't have any information about the sensitive attribute Z. So this is a case where the output is also causally fair because it doesn't depend on Z. But for the example on the right, the output Y hat has some information about this gender Z that is not present in this critical feature U, because the XC is just U and Y hat is Z plus U here. But interestingly, conditional mutual information is the same for both of these examples. So conditioning only on the critical feature is not able to distinguish between these two examples Whereas from a fairness point of view, we would like a quantity that is 0 in the first case, but not 0 in the second. And so this is the desirable property, that we want to be able to distinguish between these two cases. And this unique information measure enables us to do that. So this is the formal definition of unique information. It's the minimum conditional mutual information when only the marginals between zy hat and zxc are preserved, but the joint distribution of these three random variables are allowed to vary. And if you're interested in Venn diagrams, this is a Venn diagram interpretation of unique information. So it is essentially the intersection between just dependence and conditional dependence that would go to 0 whenever either of them would go to 0. And this unique information satisfies the causal fairness property as well as this other property. So unique information is a good measure for computing this non-exempt disparity, and it's also observational in the sense that until now we have not yet leveraged the causality structure or the causal model or anything like that. It does have some nice properties, but then there are some more nuanced scenarios that even unique information is not able to address, which is this case of masking. So what is masking? So we look at the example of masking. Now let's say a hiring ad is shown to men with high inner ability and women with low inner ability, and it is not shown to these two fractions of people. And let's say that all these four fractions or groups are equally balanced. So this can be mathematically written as an XOR, where the output is Z XOR U, and both Z and U could be Bernoulli half. So this is a scenario where the statistical disparity is 0, but this model is not exactly causally fair because this gender Z still has a causal influence on the final output, even though from observational standpoint, we do not see any disparity, and we would find that Z and Y hat are statistically independent, even though there's a causal dependence from Z to Y hat. So to capture these kinds of more nuanced examples, we include another desirable property that the non-exempt disparity should be non-zero for this kind of example to be able to detect this perfect masking. And finally, we have one causal measure that satisfies all of these desirable properties, including masking. So this measure is the unique information where UA and U, where U is the set of all possible latent random variables in our system, and UA and UB is a partition of all of those latent random variables. And as you can see, this measure depends on the causal structure and requires knowledge of the latent random variables. But we're able to show that this measure satisfies the properties that I talked about, as well as some natural monotonicity properties as well. Like if all the features are critical, it will be 0, and it's monotonic as we include more and more features in the critical set, and it becomes 0 if none of the features are critical, then it's equal to the total causal unfairness. So again, as I said, this measure depends on the latent random variables and on the causal structure. But we believe there is some value to first finding a measure that actually captures, satisfies all the desirable properties, however complex it might be to understand or compute, because then it can serve as a benchmark for all these other observational measures and help us understand to what extent they are close to the original measure. And another important aspect is that the unique information, the observational unique information measure that I talked about is actually lower bound for this measure. And it is actually good enough for a lot of situations, except to capture these kinds of perfect masking scenarios. And it is only to be able to capture these kinds of perfectly masked scenarios that we need to go into this latent random variable, understand these latent random variables and causal structures.
Quick question.
Yes.
I just want to clarify the statement here. So you're saying you give any causal graph with any number of latent variables going in whatever direction you want. This is guaranteed to satisfy these 6 properties.
Yes, this quantity will satisfy these 6 properties. And these properties are stated informally in the talk, but they are written formally in the. So I try to give some intuition on the proposed measure. So one might first think that is non-exempt disparity guaranteed if all causal paths from Z to Y hat pass through the critical feature. But we'll have this kind of examples with some confounding effects where this may not always hold. So this is a case of disparity amplification, where again we have these two features Z plus U and U. But this time the model does something weird. It can subtract out U and only begins to base its decisions on Z. So this is a case of disparity amplification where seemingly less biased features are mixing to produce a heavily biased output Y hat, which is equal to Z. And here these kinds of causal paths are passing through XC, but this U has this kind of a confounding effect, which is causing this problem. So in general, there can be three types of latent random variables: ones that only influence XC, ones that only influence Y hat, and ones that can have this kind of a effect on both of them. Now, when this third kind of random variable goes away, latent random variable goes away, we can choose UA to be U1 and UB to be these variables. And this kind of a conditional independence will hold. But then when we have all these kinds of relations, like U3 is there and Z also can have other paths to Y hat, then this conditional independence may not hold for all partitions of UA and UB. So then we saw that conditional mutual information can sometimes capture misleading dependencies. So we use unique information as our proposed measure. And this gap denotes the kind of misleading dependencies that could arise when we do not really want our measure to be non-zero, but the conditional mutual information happens to be non-zero. And this is also an upper bound for this measure of unique information that we are trying to compute. So in essence, this gives us non-negative decomposition of the total causal disparity into exempt and non-exempt components. But we have a subsequent decomposition in the paper as well, which further decomposes this total causal disparity into 4 components, that is visible and non-exempt and visible exempt, and also masked non-exempt and masked exempt. And one aspect about this kind of decomposition is that this is a non-negative decomposition. So unlike causal decompositions where the components can be positive or negative and they could add to something, but here all of these components are non-negative. So if the total causal disparity is 0, all of the things inside the Venn diagram also become 0. So then we move on to observational measures, because this measure required the knowledge of the latent random variables. So what can we do from a purely observational perspective? And as we might expect that we have this impossibility result that purely observational measures cannot satisfy all of these 6 desirable properties. But with some partial knowledge or assumptions about the causal relationships, they can correctly quantify non-exempt disparity. So these are some observational measures that we could use potentially for scenarios where the causal latent structure is not known. I've already talked about mutual information and unique information. And this is like a more heuristic kind of mutual information where you could, if you have partial knowledge about some random variables, you could choose to condition on some more random variables than the critical feature. And then we have some case studies for auditing as well as training, where we use these observational measures of non-exempt disparity. So we get these kinds of, we use simulated data first, because for simulated data, we actually know the ground truth and we can compute our measure. So we are able to compute total causal disparity as well as compute these kinds of exempt and non-exempt disparities. And when we use them as a regularizer with the loss function, these are the kinds of plots we get. Like we find that accuracy decreases, and these regularizers also tend to decrease the original non-exempt disparity. This is the actual causal measure of non-exempt disparity, and we are seeing how well these observational regularizers are able to reduce that. And again, for computing them in practice, I've used a lot of approximations. Like I've approximated them using correlations and made some Gaussian assumptions. But so there's a potential for even improving the estimators for these quantities. Then we also look at other scenarios where there's actually no causal disparity. Here we see mutual information falsely tries to reduce non-exempt disparity when there isn't any, but unique information doesn't. And then these are other scenarios where there's some masking. And in masked scenarios, sometimes conditioning can help reduce some kinds of masked disparities, which unique information again doesn't address. And then these are some experiments on real data. Again, because these regularizers are observational, they can be computed on real data, but it's difficult to verify whether they're actually reducing the original non-exempt disparity because we do not know the structural causal models here. But nonetheless, these observational relaxations can be used for auditing or training purposes. And we also performed some experiments on the CMU EC graduate admissions dataset, where we looked at these quantities, the observational quantities, and looked at a partial information decomposition of mutual information and conditional mutual information on the admissions dataset. So summary before we move on, this work provides a systematic approach to finding a measure of non-exempt disparity. And conditional mutual information or naively conditioning on features can falsely detect disparities, even if they are causally fair. But unique information doesn't falsely detect disparity, but then it can sometimes miss these kinds of masking effects. And there's potential for future work, like finding improved estimators for these quantities, as well as some broader conversations that this work opens, like how do we interpret or understand laws for algorithmic hiring? And it is essential to collaborate with lawyers and social scientists to be able to fully understand this picture of algorithmic fairness, where there's like critical features, and then there are some disparities which are exempt and some disparities which are not exempt. So now I'll very briefly mention some other problems that I'm also working on. So this is a problem, this applies the similar kinds of ideas to a different application, which is the problem of filter bubbles in social media. So filter bubbles refer to a state of intellectual isolation where a user is only exposed to content that you like and agree with, and you do not get to see the other side of the debate. Like if you like New York Times, you get recommendations from New York Times. If you like Fox News, you only get recommendations from Fox News. So here we use this idea of computing exempt and non-exempt topic biases, where a user gets to select certain topics that are really critical or important for them, whereas there are some topics that are less important for the user. And we're able to compute these kinds of exempt and non-exempt topic biases using a similar idea. And this is another problem that I've been looking into. This is slightly different from the problem that I was talking about, because this uses some other measures of fairness. But this is a question on, is there a trade-off between accuracy and fairness? This is a problem that is also gaining significant interest in the fairness community. And while there have been several empirical and theoretical papers that have pointed out towards the existence of this trade-off, but there's been relatively less work on how do we quantify this trade-off, or how do we understand how much does accuracy fall for how much reduction in bias or disparity. So in this work, we use these tools called Chernoff exponents as approximations to the actual error exponents in binary classification. And the nice thing about Chernoff exponents is that they have a nice geometric interpretability, which helps us quantify the trade-off between accuracy and discrimination in terms of these Chernoff exponents. So here I use a measure of fairness which is close to equalized odds or equal opportunity, which is the equality of false negative exponents for the two groups. And a sweet spot will be here, that is, we want high accuracy and low discrimination. And we introduce this concept of separability, which using Chernoff information, which quantifies the best possible accuracy exponent that you can get for a particular group. So then we're able to compute these kinds of trade-offs, where the optimal but unfair classifier would be over here. And the fair but suboptimal classifiers would be somewhere over there. And we also show that if we're able to somehow get more information about the data set, like either through gathering more features or refining your experiment, then sometimes the separability can possibly improve. And if the separability or information theoretic bound improves, then the trade-off can also be alleviated. So now the optimal but fair classifier, unfair classifier would be here, and the fair but suboptimal classifier would be over there. And we also show that there are ideal distributions with respect to which there may not be any trade-off. So looking forward, these are some questions that I'm interested in. One question that I'm particularly interested in is this feature engineering or problems in the feature selection space. Because the problem is not always very neat and clean where we have a set of features and we just have to make the model fair, but even in the feature engineering space, there can be thousands of features and there can be a lot of debate on which features could be used, which features couldn't be used. And then there could be further debates on whether this feature is contributing to the bias or whether this other feature is contributing. So that's another space where I'm very interested in. And there are also problems like training models with restricted access to certain features, like you're not able to use gender, race, or even zip code to be able to train your models or to make them fair. Then another problem that I'm also getting interested in is this problem at the intersection of partial information decomposition and causality. So this is not really related to fairness, but generally I want to understand whether partial information decomposition has an interpretation in causality or causal DAGs. For instance, in these two situations, the conditional mutual information is greater than 0 in both these cases, but when C is a child of both A and B, then the unique information becomes 0 and the entire information is synergistic information. Whereas when it's not a child in that kind of setting, the synergistic information is 0, whereas the unique information is not. So yeah, my research vision is to build the foundations of reliable machine learning that are deep rooted in foundations of information theory, causality, and statistics, and connecting it to different applications. So thank you so much.
Any questions?
I guess I was thinking about for your earlier examples, and like you had this causal fairness which had to do with these different variables, but when I don't know, or whatever, I guess is coming up with an algorithm that doesn't have access to that same variable, but it's when it has to be audited, like against those, is there a way of kind of measuring the metric of like that unfairness that's due to the fact that this unobserved variable is, is latent, as opposed to what's the amount of fairness that could be closed algorithmically? Sorry, did that make sense? So like I could have a like the minimum unfairness I could get limited to the fact that I'm only allowed to use observed data versus that might already be a non-zero unfairness. Right. So but then there's an additional like unfairness that comes because I'm using that algorithm. And is there a way of like distinguishing that? Do you have any insight?
Yeah, so what you're saying is like, suppose you know that you will not have access to the latent random variables, then can I give guarantees on this much fairness I can still remove, and this is the part of fairness that I'll be not able to remove. Okay. Yeah, I think this lower bounds that I was showing before, the unique information, let me go back. Yeah. So here, this unique information, this is actually, this one is an observational quantity. So you could remove that much of unfairness surely. And this will be like, this gap will be like the extra unfairness that you're not able to remove. But then there are also like upper bounds that are observational. So you could also remove more unfairness, but at the cost of falsely removing some dependencies or falsely accounting for certain dependencies. I don't know if that was your question. Yeah. Okay.
Any other questions? So
So you found this approach that people in information theory do, where they propose axioms that do one thing to satisfy it, and then you derive the thing. But with fairness, you can argue about these things, about what axiom, how do you think about that? What if somebody comes to you and says, I don't believe in axiom number 3 that you propose in my application? Or how does that tie to examples? Like, did you experience in various settings where like only some axioms are satisfied, not others?
Yeah, that's a good question. Yeah, so I think even when we use these kinds of observational relaxations, like this previous example that I was talking about. So here, if we do not care for, say, these kinds of scenarios where like perfect masking is happening, then we could probably drop this axiom and say these are 5 axioms and maybe an observational measure will satisfy these 5 axioms. So that could happen. And I feel that these axioms are also, each axiom is connected to some set of canonical examples, and they give some insight on what kind of fairness you want in one particular scenario or one particular distilled scenario where other kinds of dependencies are not arising. So as long as you are interested in addressing that particular kind of dependency, you might want to include that axiom. But I agree with you that, I mean, there's no guarantee as such that these are the 6 axioms that should be followed, or like there are no other possible axioms, or why we shouldn't just drop one axiom. Because yeah, even some of the observational measures are not satisfying all 6, they're satisfying any 5 or any 3. So I think these axioms help you group canonical examples in some sense into different categories.
Do you have any sense that there are other measures that can satisfy all of these assumptions, or is this?
Yeah, so I think, yeah, that uniqueness is also something that is not yet shown. So yeah, there could be other measures that also satisfy these 6 axioms, yes.
Any other questions? All right, let's take this speaker one more time.